chair the session, but I think that we should start. So, in this session, we will focus on how the immensity of the heavens was tamed and brought down to a human scale through technological ingenuity. We will examine planetary movements and how the vast distance of spaces were collapsed through the optical precision of telescopes. Our first speaker is Günther Oestmann, that I invite to Okay, so Günther has been trained as a clockmaker and received a PhD with a study on the astronomical and astrological significance of the clock in the Strasbourg Cathedral in 1992. In 2013, the Museo International de l'Horlogerie in La Chaux-de-Fonds awarded the Prix Gaia to him, and in 2014, he was elected as corresponding member of the International Academy of the History of Science in Paris. 3 years later, Oestmann was appointed as extraordinary professor for history of science at the Technical University in Berlin. Parallel to his academic activities, he is working as a restorer of clocks and scientific instruments. Among his fields of research are the history of scientific instruments and clocks, the history of astronomy and astrology, and mathematical geography and maritime history. So, please, Günther, his presentation is entitled Representing and Understanding Celestial Movements on a Comprehensible Scale, the Application of Equatoria and Gearing Mechanism to Clocks.
Yeah, first of all, Maddalena, thanks for the kind introduction and for the invitation to Florence. Thanks very much again. As you have noted from the title here, the title has been changed slightly. My paper will deal with the application of equatoria to clocks and the construction of planetaria. It's only a slight change. All fixed stars seem to rotate eternally with uniform motion, describing perfect circles around the celestial poles. However, the sun and moon violate the principle of uniformity by moving sometimes faster, sometimes slower through the signs of the zodiac, and the planets Mercury, Venus, Mars, Jupiter, and Saturn, known at that time, also show standstills and retrogrades. They describe characteristic loops of different sizes in certain parts of their orbits. Under the axiom of uniform circular motion, these irregularities had to be explained as the result of the combined effect of circles or spheres rotating at a constant speed. The mathematician Eudoxus formulated the first model, which consisted of a set of spheres, one for each planet, arranged concentrically to the Earth and rotating around different axes. This system of homocentric spheres became the basis of the Aristotelian universe. Here is a circular diagram of the cosmos in Peter Appian's Cosmographicus Liber, the first edition of 1533. A century later, the mathematician Apollonius of Perga introduced two new concepts of great significance: the eccentric circle and the epicycle, whose center lies on the circumference of a concentric circle, the deferent. At the same time, he proved the mathematical equivalence of the two geometric constructions. In this way, the postulate of reproducing celestial motion by a combined circular motion was fulfilled, albeit with a significant modification that contradicted Platonic or Aristotelian thinking. It was established that the observations could only be satisfactorily represented, even within the wide limits of accuracy applicable at the time, if the postulate of uniform motion was abandoned in the case of the eccentric deferent. In the new model, the rotation of the epicycle on the deferent only appears uniform from a fictitious point E called the equant, punctum equans. This lies on a straight line that connects the Earth T with the center of the deferent in C, and it bisects the distance Earth equant. Each planet's position is thus characterized by a direction in space called the apsidal line, and three equally distant points: the Earth, the center of the deferent, and the equant. However, the introduction of the equant is incompatible with the Aristotelian axiom of a uniform circular motion. The combination of an eccentric deferent with an epicycle formed the basis for the planetary theory of the Alexandrian astronomer Ptolemy in his mathematical syntaxis, written about 150, which we now refer to by its Arabic name as the Almagest. Here is a fictitious portrait of Ptolemy by Jörg Sürlin the Elder from the series of busts of prophets on the choir stalls of the Minster, about 1470. For the movement of the sun, Ptolemy adopted the theory of his predecessor Hipparchus, who had set the Earth eccentrically by 1/24 on the line of apsides, resulting in 4 unequal length quadrants of the seasons. For the upper planets, Mars, Jupiter, and Saturn, the aforementioned combination of eccentric, deferent, epicycle, and equant was used. Things became more complicated with the moon, however. The same goes for the planets Mercury and Venus. The moon moves from east to west on an epicycle that orbits the deferent in opposite direction of rotation. However, the center C of the deferent is not fixed, but rotates around the Earth in T. T forms the punctum equans in Ptolemy's lunar theory. It follows that the distance of the moon from the Earth in the quarters, that is in quadrature, is only half the distance at new or full moon, that is in conjunction or opposition. The size of the moon would therefore have to fluctuate considerably over the course of a month. This clearly contradicts experience. This problem could not have escaped the attention of astronomers. Nonetheless, Ptolemy's lunar theory formed the basis for astronomical calculations for more than 1,000 years because it reproduced the motion of the moon in ecliptic longitude with astonishing accuracy. Mercury and Venus cannot move very far away from the sun. The angle known as elongation is 46 degrees for Venus and 28 degrees for Mercury. The orbital period of the epicycle on the deferent is equal to 1 year. Mercury orbits on an epicycle from west to east on an eccentric deferent with its center in C. The movement of the epicycle center on the deferent is uniform in relation to the equant, point E in the diagram, which lies on the circumference of a small circle around Z and halves the distance between Z and the Earth, which is located in T. This gives the deferent an egg-shaped form, as you can see here in the print of the Theorica Planetarum. Ptolemy presented a separate model for the movement of each planet, and there is no reference to the so-called Ptolemaic world's view anywhere in the Almagest. However, this is by no means a mere theoretical construct, as has long been assumed, because Ptolemy certainly recognized the physical reality of the planets and their movements, and in his Hypothesis Planetarum which has only survived in its entirety in Arabic translation, with the Arabic title Kitab al-Manshurat, translated the book of sawed-off pieces. Ptolemy presents a physical description of the cosmos, in particular the nested planetary spheres, their relative distances, size, and movements. He explained that whole spheres were not necessary to represent the motion of the planets and of all celestial spheres, with only one exception, the sphere of the fixed stars, and all the other movements could be replaced by so-called sawed-off spheres. These are ring-shaped structures similar to a tambourine. Ptolemy's geometric models were crying out to be translated into geometric constructions were crying out to be translated into mechanical models. There was a tradition of spheropoia, the study of spheres, dating back to antiquity, the legendary sphere of Archimedes and the mechanism of Antikythera being famous examples. The term spheropoia had numerous definitions in ancient Greece. According to Geminus, 1st century, could refer to a subfield of mechanics, the design of astronomical models, a certain astronomical instrument, a spherical theory of the world, or a spherical system that actually exists in nature. In his Hypothesis Planetarum, Ptolemy also referred to the spheropoia. His aim was to deal only briefly with the theories in this treatise. These were treated in more detail in his Almagest. For ourselves, that means astronomers, as well for the makers of instruments, which are mentioned here explicitly. But these were not mere craftsmen. They were rather those who designed models of planetary motion. Ptolemy distinguished between the construction of complex astronomical models that illustrated the underlying theory of planetary motion and a so-called common branch in which the underlying reality was disregarded and only the phenomena were displayed, that is, the apparent or mean celestial movements. And here the focus was on the skill of the craftsman. Ptolemy does not provide more details. He only speaks about a simple arrangement, possibly with rotatable disks, in which a planet could be moved by hand to the appropriate position for a respective date. This type of instrument probably resembled the so-called equatorium used in the Middle Ages for determining the position of the planet in terms of ecliptic longitude and latitude without requiring calculations. The other design mentioned by Ptolemy combined numerous individual models using a so-called mechanical approach, which were presumably connected to each other with gears, such that the motion of the entire system could be represented mechanically. However, Ptolemy does not provide any details for either. The first Latin treatise on the equatorium was the work of Campanus of Novara. This text from the second half of the 13th century was the first Western exposition of the Ptolemaic system and also offered specific instructions for the construction of equatoria. Campanus conceived his instrument as a pedagogical aid to his book on the theory of the planets, and it was introduced in university teaching. Here's a beautiful example by the cosmographer Sebastian Münster, an equatorium for Mercury about 1520. With the advent of printing, the equatorium became more widely known, reaching its culmination with the publication of Appian's sumptuous Astronomicum Caesareum in 1540, only 3 years before Copernicus' De Revolutionibus appeared. Here, an example, the Mars equatorium from Appian. The mechanical clock had barely been invented when the first attempt was made to mechanically set equatoria in motion in order to display the motions of all the planets in a clockwork mechanism. The Italian physician Giovanni de Dondi is the author of various medical and literary works, but his fame is linked above all to the creation of the astrarium, an astronomical clock constructed about 1365 to 81, of which he also left a detailed description with drawings, the Tractatus Astrarii. He followed the Theorica Planetarum by Campanus, and like his Equatoria, the astrarium implemented the representation of the movements of each planet in an independent mechanical element. Dondi personally carried out and described every step of its construction. Unfortunately, the astrarium is not extant. It perished in Milan, but thanks to Dondi's detailed descriptions, preserved in a number of manuscripts, a number of reconstructions have been executed. This is one of these reconstructions, this one in the Smithsonian Institution. Dondi's astrarium looked like a heptagonal tower divided vertically in two sections. The lower one housed the clockwork, that is the driving apparatus, with verge escapement designed to move every part of the machine, consisting of a horizontal wheel with 365 teeth, centered on the axis of the tower and rotating at the rate of a common year. Above, a set of 7 vertical dials were arranged, driven by wheels meshing at right angles with the main horizontal wheel. Each dial offered a precise mathematical transposition of Ptolemy's theory of planetary motion. In the fixed zodiac ring, the respective mechanism with the epicycle circle and ruler moved, on which the body of the planet was placed. Here, the dial of Mars as an example of this reconstruction. The peculiarities and irregularities of the theories of each planet, particularly Mercury and the Moon, and the compound mechanism of the Sun's daily movement were reproduced through complex gear trains, even using oval wheels. Here an example from one of the manuscripts. Dondi's astrarium combined the Arabic tradition of miniature models of the universe, that is, astrolabes and equatoria, and which constructed so-called proto-clocks, and with the new technology of mechanical clocks spreading in Europe since the early 14th century, also these astronomical models became more widespread. Dondi's astrarium was simultaneously a clock, an analog computer, and a demonstration device. It allowed the movements of celestial bodies to be read without calculation, and it translated Ptolemaic astronomical theory into a mechanical model. What about the heliocentric system of Copernicus? First of all, the widely reproduced schematic representation in Book 1 of De Revolutionibus has often led to the erroneous interpretation that Copernicus conceived a system that was considerably simplified compared to Ptolemy's. However, this is not the case. Like his great role model, Copernicus consistently assumes uniform circular motions of the planets and uses eccentrics and epicycles. Here's the schematic drawings, how the combined systems of planetary motions in Copernicus, De Revolutionibus would have looked like. There is no diagram whatsoever of this kind in Copernicus' book. The first attempt to create a model was made by the Freiburg mathematician Erasmus Oswald Schreckenfuchs in 1468 to 9, and he intended to represent both the Ptolemaic and the Copernican hypotheses. Tycho Brahe denied that this was possible, and unfortunately it is unknown what form Schreckenfuchs' planetary model possessed. There are no details extant. Kepler thought of the display of a simplified planetary arrangement in 1598 to 9, and he offered a materialization of his idea to the Duke of Württemberg. We have seen this already. Of Kepler's planet chalice, or Kredenzbecher, only a rough drawing by the Tübingen astronomer and Hebraist Wilhelm Schickard exists. We have seen this already. And in his sketchbook, the picture is shown here, Schickard describes it as follows. I've translated the early modern German text. Cup showing the movement of the planets. At the bottom is a large wheel with 4 times 365 teeth, which revolves in 1 year. It drives the small wheels of the mean movements of the planet. These moves a tube. Each has an iron arm with a planetary symbol on at the top. On the top edge is the ecliptic. The upper rete is painted on glass. The creator of the whole thing is Kepler. Kepler greatly underestimated the mechanical problems involved. It would have been almost impossible cutting a wheel of well over 1,000 teeth in a comparatively small size. And his design proved unworkable on this scale. So the project of the very first Copernican planetarium was never realized. It should be noted that the geoheliocentric system of Reimarus Ursus, this was an attempt to find a compromise solution between the systems of Ptolemy and Copernicus, has also been represented in a model. The original, executed by Just Bürgi, is not extant, however. 10 years ago, the Dittmarscher Landesmuseum in Meldorf commissioned a demonstration model of Ursus planetarium with a manually operated crank drive, which has been executed in my workshop. This is the model. The second copy has been made for the Tsinghua University Science Museum in Beijing 2 years ago. Between 1650 and 1664, Duke Frederick III of Gottorp commissioned the creation of a special building, a globe house, which housed a giant globe of about 3 meters in diameter. This monumental globe was widely known and admired by many contemporaries as a wonder of the world. The globe house is no longer existing. This is a reconstruction of my friend and colleague Felix Lüning. And here you can see the globe with a water wheel drive, also reconstruction. The idea to build the globe probably came from Duke Frederick himself, but the scientific management of the project was in the hands of his learned court mathematician and librarian Adam Olearius. He was keenly interested in the construction of clocks and scientific instruments. He made a telescope and microscope himself, developed a method for grinding lenses, and took a self-made astrolabe on his diplomatic mission to Persia with him. Olearius worked with a team of craftsmen from various trades: blacksmiths, locksmiths, watchmakers, copper engravers, carpenters, and painters, and also lent a hand in this ambitious project. The globe rotated using water power. It had a walkable horizon ring and showed the starry sky as it is visible from the Earth. Visitors could climb into the sphere through a hatch, sit down on a bench, and watch the sky revolve around, which was illuminated by candlelight. The sun, in the form of a crystal, moved automatically through the zodiac in the course of 1 year. The Gotthard globe represented a materialization of the geocentric worldview, but Olearius emphasized the educational value of the terrestrial and celestial globes as demonstrative models and representations of the Earth and the cosmos, in which the Creator God and his omnipotence could be recognized. As a counterpart to the Gotthard globe, a Copernican planetarium, the so-called Sphera Copernicana, was executed by the Limburg gunsmith Andreas Bösch and the clockmaker Hans Schlemmer between 1654 and 1657. A highly complex gear mechanism driven by a single clockwork served to illustrate or to demonstrate the movement of the planets. Here's a detail. The interior. The planets revolved within an armillary sphere with the figures of the constellations, and the whole was crowned by a small Ptolemaic system, also in the form of an armillary sphere. Back again to the total. You can see it on top of the heliocentric sphere, a tiny Ptolemaic sphere. Erhard Weigel, professor of mathematics at the University of Jena, described a so-called pankosmos in 1671 with dimensions approximately matching those of the Gotthard globe. It is quite likely that he was familiar with the latter, but this has not been proven. In 1696, Weigel presented another pankosmos to the Danish King Christian V, and the third object of this kind is said to have gone to the Imperial Court in Vienna. None of these globes have survived, however, and only very superficial contemporary descriptions are extant. The Gotthard globes and Weigelstein globes were Baroque world theaters that can be considered precursors of today's planetaria. They most likely served as models for the giant globe erected in 1758 at Pembroke College by Roger Long, a Cambridge astronomer. These large-scale objects were rather exceptional, however. In the 18th century, small, transportable models played a more important role. Newton's scientific achievements were now omnipresent, his universal theory of gravity having provided an explanation for the orbits of the planets. The great interest generated a flood of generally understandable presentations, and high society enjoyed engaging in astronomy. This was considered particularly suitable for promoting rational thinking and stimulating contemplative reflections on God's creation. A variety of mechanical models of the heliocentric planetary system, so-called orreries, were built and presented to the public by itinerant lecturers. The name derives from Charles Boyle, 4th Earl of Orrery, for whom the first instrument of this kind was built by John Rowley in 1713. These devices were very popular at the time. They were used to illustrate phenomena such as day and night, seasons, moon phases, eclipses, and so on. A light source was placed in the center to represent the light of the sun. But they could not be to scale, however. Whereas the relative sizes of the planets could be represented approximately, the relative distances of the planet from the sun and between them were far too great to be displayed properly. However, such teaching aids help to convey the new mechanic explanations for the movement of the planet, and they inspired awe for the position I'm just about to finish of mankind in this clockwork universe. And I would, here's the planetarium by Rowley, the first one, and I would present the first slide. In 1766, the painter Joseph Wright of Derby depicted the didactic significance of models of the cosmos in an evocative painting. Astronomy is portrayed here as a social activity in which children as well as adults can participate. In the semi-darkness of a library, illuminated only by a single light source, a group of people have gathered around a planetarium in which tiny planets orbited by their moons revolve around the sun. The lecturer points to the moons of Jupiter while a man eagerly takes notes. Two children follow the demonstration spellbound while one listener is visibly lost in thought. The lamp standing in place of the central sun not only casts its light on the faces of those present, the vivid demonstration of the science of astronomy also illuminates their minds. Thank you very much.
Thank you so much, Gunther, for this fascinating presentation. I'm sure that afterwards we will have plenty of questions. So now I'm going to introduce Giorgio Strano, that we all already know. He is the head of the collections at the Museo Galileo, and is actively involved in the study and popular dissemination of the history of astronomy. Some of his national and international publications in reviews include Nuncius, l'astronomie, Acta Historica Astronomiae, la nuova informazione bibliografica, Automata, giornale di astronomia, Sterne und Weltraum. In addition, he has collaborated in the following exhibits: Scienziati a Corte in 2001, Vitrum in 2004, Macchina Mundi, same year, 2004, Galileo's Telescope, 2008, and then Italian Hours, Historical Clocks from the Del Vecchio collections in 2023. From 2007 up to 2020, he has been general editor for the series Scientific Instruments and Collections published by Brill. And today he's going to celebrate Cassini's 400th birthday, which was one of our aims with this conference. And his talk is precisely entitled Cassini's Preference for Campani's Telescopes.
So it's a dirty job, but someone had to do that, to celebrate Cassini inside the museum. So thank you. I will say thank you for the invitation to stay here in Florence. But so we start directly with this stamp that reminds us that this is the fourth centennial from Cassini's birth in France, Italy of the time, in Perinaldo, that was in the French domain, but is in Italy today. And Cassini went a better fate in stamps than our patron here at the Museo Galileo. We have a stamp from Gibraltar for the 209th year of astronomy. But I will start with Galileo, because I am speaking of telescopes. So this is Galileo at the time, and one of his creations that you saw yesterday here in the museum. And Galileo was the improver of the telescope that was invented in the Netherlands 1 year before, in 1608. So Galileo was able to increase the magnification of the instruments and made the instrument very popular with his correspondence, and many people asked for Galileo's telescopes. But he also left an heritage to some of his pupils, like Evangelista Torricelli, that made telescopes in Florence, and that also emphasized the fact that telescope objective and lenses as masterworks that have to be signed and dated. And then other continued the tradition, moving from in other cities. For instance, Francesco Fontana, that was one of the first to build Keplerian telescope, different from Galileo's. And now we move directly to the telescope in the second half of the 17th century. And we start with Divini's against Campani. That is the first step in a story that usually is not well represented in the former books. For instance, Van Helden, in his contribution to the activity of the Cimento Academy, doesn't mention this part of the story. It appears in the last book, for instance, by Bedini, that has been published posthumous a few years ago. So, and everything started with the Pope insomnia and his need for a clock that was silent and that can be consulted without lighting a candle. And the solution came from the three sons of Angelo Campani. And the first son was Matteo Campani. He was just a priest, but introduced in the Vatican and with acquaintances between the people connected to the Pope. And the real genius of the family, as is called in Bedini's book, Uncommon Genius, Giuseppe Campani. And the third brother, that was Pier Tommaso Campani, that continued his life as a clockmaker, but very quickly was separated by the other for internal controversy within the family. And where Divini came in? Divini came in criticizing the realization made by the Campanis. They made the clock, the silent clock, but Divini started to say that it was not an invention, it had been already invented. Others came in, as Francesco Chinardi, that a few years later claimed that he has already done a silent clock using the same silent escapement than the Campanis. So the Campanis were quite upset, and they remembered what happened before. So let's move to Divini himself. Divini, in between 1640s and 1660, was the master in making telescopes in Italy. Here is Divini in a publication by Carlo Antonio Manzini, L'Occhiale all'Occhio, that prized Divini for his ability in making telescope. This is one of the telescopes that is here in the Museo Galileo, done in around 1664. And Divini published also an advertisement sheet that unfortunately I didn't brought down. It is upstairs. I prepared it, but I forgot, sorry. And with the discoveries and the observation the observation that can be done with his telescopes. Like Saturn is as described by Galileo, the moon as the Venus as a crescent, the map of the moon with the craters, and the bands of Jupiter with the satellites of Jupiter. So this is the book by Manzini that refers to Divini's workshop, also describing the tools and the machines. Actually, these are those from Divini, but also those from Campani, but about how to make the telescopes. And the first problem that Divini met was Christian Huygens and his explanation of the strange observation made by Galileo has a ring, a solid ring around Saturn. Well, you can see here the thickness of the ring here, and also Huygens' discovery of one first satellites of Saturn that you can see here. And those discoveries were made, so Huygens said, by the help of a new type of ocular invented by Huygens, by Christian Huygens, and by his brother. So Divini was immediately upset by this and reacted, and unfortunately he joined a Jesuit priest that was Honoré Fabry, that was writing reactions against against Huygens' discoveries, and the signature of the publication was, however, by Divini. So you can read the Stacchi Divini and this attack against Huygens, but actually the book was written by Honoré de Fabry. So the result was that disaster for Divini, because trials were made also in Florence to check which theory was correct. The ring of the satellite supported by Divini, and that produced a strange appearance in Saturn. And Divini was defeated by these tests. So, but now we enter directly in the conflict between Campani and Divini. So there we had the action, Divini against Campani, but now we have the reaction, the Campani's against Divini. And their action was pretty stronger than the first attack by Divini. So they started, the Campanis, Matteo and Giuseppe, to go around Rome with a telescope that was supposedly made by the Huygens. Perhaps it was coming from we thought it was coming from the Lower Countries, but actually was made by Giuseppe. Then between 1662 and 1673, they started a series of paragoni, they will call, also called in Italian, confrontation between the Campani's telescopes and the Divini telescopes. But all the paragoni were performed by the Campani at the beginning, so all in the advantage of the Campanis and not of Divini. So Divini reacted once again. They were craftsmen, they were very proud of their works, and easy to react one against the others. And Divini wrote to Carlo Antonio Manzini this letter that was published. The Italian is very poor, so you can actually understand that Divini was not well prepared to react to anything. And in this booklet, he claimed that he had a new type of telescope with an ocular that is made of 3 lenses that produce a larger field of view, less chromatic aberration in the images, and upright images. And he wanted to challenge the Campanis, and here you see, let's therefore do the test with a wager, either big or small, and as I am pretty sure to win, I commit myself to some pious work, such as, for example, to marry some spinters or buy a bell from some poor church. And again, and if I lose, I want to lose 100 doubloons, and if they lose, I will be satisfied with 100 scudi. So 1 doubloon was a golden coin, and 1 scudo was a silver coin, so you can understand the difference. But again, and here is where Cassini came in, on October 1633, there was a real paragone with Cassini present, and the result was pretty ambiguous. Campani's telescope made the observer objects clearer, but Divini's telescopes made the objects larger. They continue, another paragone, Campani was still present, but started also to have, Cassini was present, but he also started to have a relationship with the Campani. They discussed it, they were able to see things better than any other and during the paragone. And Campani's telescope was perfectly mounted, and Divini's telescope was just put on some chairs. So you can see how objective were these paragoni. So, and where Campani started to be very known is because of a new observation by Cassini by using Campani's telescopes. This is the Ragguaglio of about two new observations written by Giuseppe Campani, but perhaps by his brother Matteo, that was the priest better able to write than the brother. And you can see the shadow of the planets on the ring here, and the shadow of the ring on the planets, an interesting, important observation. And made by, of course, by Cassini. And another discovery that by the bands of Jupiter that can be seen with the Campani's telescope. Of course, they have been already discovered by Fontana, but that is another story. And another discovery that the relief on the edge of the moons can be observed with the Campani's telescopes. And an advertisement sheet from Campani against with another observation made by Cassini of the shadows of the sun-moon of Jupiter on the body of the planets. The paragoni continued for another year, and this is when the Accademia del Cimento came in, and the Cardinal Leopoldo de' Medici and his brother Ferdinand II wanted to know which was the best maker, Campani or Divini. So they started to prepare inside the Accademia del Cimento test sheets for observing and deciding the quality of the telescopes. They started with words and verses. They continued with the random letters in words, and then they finished with what we would call the prototype of the modern octotype, with just letters of different size that had to be identified with the telescopes. The final paragone took place in December of 1669, and Cassini was not present, but one person from the court of the Medici was present and sent a report. If you want my opinion, I don't know, because the difference between exquisite things are small, so the telescopes were almost equivalent. And we made tests about these telescopes, the lenses between 2008 and 2009, together with the National Institute of Applied Optics in Arcetri. The lenses were measured, the composition was studied, the surface was also studied with different tests. And this in particular is a micrograph of the surface of an objective by Campani. Note the grinding. And this is another examination of the surface of a lens by Divini. And what was the conclusion? That the lenses and the telescope was almost equivalent, but with different approach to lens making. Campani just tried to make very spherical surfaces in spite of final polishing. So you can see these relics of the grinding grains during the grinding. And Divini wanted to have very polished surfaces, but as a counterpart, the surface was not perfectly spherical. But the results is almost the same. So what happened was that the Campani's success was directly connected to Cassini's success in making observation. let's resume the whole thing. So Cassini discoveries made in Rome with the Campani's telescopes. Too quick. So Jupiter's dark bands are rediscovered, actually. The profile of the lunar mountains on the edge of the moon. In 1664, once again, second series of discoveries, Saturn's ring shadows and Jupiter's moon shadows. And finally, in 1667, Jupiter red spot and Jupiter axial rotation. Then Cassini was a professor in Bologna, so he was occasionally in Rome. Then he returned to Bologna, continued to make observation, and he discovered the spots on the surface of Mars, and also made an estimation of the rotation of Mars around its axis, which actually was an observation already made by Divini, but not well known. But Cassini mentioned it, so he knew of that. And also Divini tried to make an estimation of the rotation of Mars that was too quick in comparison to the one by Cassini. Then Cassini was called to Paris as a consultant for the building of the Observatory of Paris, not as director, as has been emphasized in the Bologna conference this year. And you can see here the members of the Academy of Science around Louis XIV. And between the members, you can see Cassini here. And looking at him is Huygens. So this is their return in our story. And Cassini discovered in Paris a new satellite of Saturn that was called Geppetto, but this is a name that was given many years later by others, not by Cassini. Then another satellite of Saturn in 1672. The so-called Cassini division today, so-called Cassini division of Saturn rings. And in 1684, two more satellites of Saturn. And an interesting discovery in 1692, that the rotation of Jupiter is not uniform, but the equator is lower than the polar regions of Jupiter. So this was published in 1692 by Cassini himself. About his production while in Paris, I mentioned this magnificent map of the moon with the curious details and a woman looking at an art. So it is a trick inside the moon chart. And unfortunately, we have only one lens clearly connected to Campani in the Paris Observatory. That is this one with a diameter of about 13.7 centimeters and a focal length of what is today, it's about 11 meters. That is comparable with the telescope that you saw upstairs yesterday, that has a length of 13.7 centimeters and a length when opened of about 11 meters. But we know that Campani also made aerial telescope like those devised by Huygens, again, Huygens once again. And so you have the objective fastened to a mast, and you have here the ocular. You pull a rope and you are supposed to have the optical system in line, and you are able to make observations. And the only one that completely survives those Campani's aerial telescope is in Kassel today, and with an objective about 21 centimeters and a focal length of about 32 meters. It is not so long. And we can see in Paris Observatory this tower with the aerial telescope, the objective, and the ocular here, and other telescopes which are not necessarily made by companies. And there is a number of lenses of Campani for aerial telescope that is preserved now in Bologna, in Palazzo Zamboni, and with a very considerable focal length. These are my pictures, so this is why they are so bad. And they went back and forth from Paris. They were examined by Cassini and sent back to Campani, and including one that was broken by an assistant of Cassini and sent back to Campani. So this is just to emphasize the fact that in order to be able to claim yourself as the best telescope maker, you need observation made with your telescopes, at least in the time of the second half of the 17th century. And if they were made by Cassini, that was a very important astronomer, it is much better. So, thank you.
Thank you, Giorgio. You can stay there, and Günther can join us for the Q&A. Do you have any questions? Okay. So I will start.
So I have a question for
Please,
Günther.
Go.
So in the cup by Kepler, there is something that can be seen in the background that looks like 2 gears. Yeah. Good.
I go. So good.
So it wasn't possible to see them in Francesco's presentation, but
So. Yes.
yeah. So here, there is something around here. So it looks like 1 gear that matches with something very strange. Did you know what it is?
What are you referring to exactly? Yeah, yes, this one. Yeah, this is, well, this shines through the page. This is, in fact, this is a drawing from another page, and it does not refer to the planetarium. It is a water pump. It's a water pump consisting of 2 gears, more or less resembling the principle of the Wankelmotor. These were arranged, I think there were moving parts in these manuscripts, cut out. Yeah.
Okay, does the room have questions? I have questions for both of you. Okay, sorry, I haven't seen you, sorry.
I have a question about the moon map of 1649. Was that by Divini? There was an image of the moon from 1649. Was that
yes, that is
Divini? Was it based on his own observations?
Yes, that was an advertisement sheet for the Gradico Tuscany. So by my telescopes, you can see such thing like this. Sorry, I have this upstairs. It's a pretty big piece of paper We made a reproduction by using the original copper plate. And I will show you after coffee break. If you like.
Yeah, that would be great.
So, but these are not advertisements. There is a number of information here. You can see to the Serene Grand Duke of Tuscany and so on. So this is what I've observed and what you can observe by using telescopes.
So it was just published like by itself, just as a sheet?
It's just
Okay.
a piece of paper.
Okay.
Yes.
It looks a little bit like Johannes Sibelius's.
Yes, it's
When-
a little bit, let's say, later.
Yeah.
2 years, I
Yeah.
think. A few-
Very interesting. Thank you so much, and
Yeah.
thank you for your presentations.
Can I ask you something? Okay, Giorgio, first, since your PowerPoint is already there, you showed a stamp with Galileo, and you have written there are 3 anachronisms. So I was wondering.
No, that
if-
could be some for having some price, but I did not think of the price. So,
Eh?
so do you see what is wrong with this?
No, I wanted to ask you.
It's completely wrong, but that is another. So this seemed to be Venice. Galileo was, yes, it was from time to time he went to Venice, but he was in Padua. This is a pretty old Galileo. You have to compare with the other portrait by Domenico Tintoretto that is in about the years of the invention of the telescope. So this is a bold individual, we don't know who this is. And then you are looking at this telescope that was made in Florence, this one, which was also coming part from France, but that is, so these are the 3 anachronisms of this, but 42 pence instead of nothing, and then for the Italian postal service for this. So you can see other things here that I didn't mention, the renovation of Dante's sundial in San Petronio made by Cassini, that you can see here, San Petronio, and here the Cassini division, but there is also another division here, so it's the usual crazy things that you obtain by these cases, and the 4 satellites of Saturn discovered by Cassini. Perhaps one of them is the one discovered by Huygens, but we don't know what they are. But
Thank you, Giorgio. And okay.
Yeah, I have 2 questions, but one for Gunther, and it's about Appian. If we can go back to the to the thing, because
It's the last one. Yeah.
Yeah, well, not this one, but the previous one, which is about the old model, I think. Sorry. Yeah. Oh no. It's
Yeah.
that one.
The cosmographical.
Yeah, because
Well, the cosmos diary.
I'm very intrigued by the small details around the not the zodiac sphere, but the 9th, because there is some gear. Yeah.
Yeah. This is a depiction of the mechanism of trepidation. It is the alleged back and forth movement of precession.
Of the precession of the equinoxes.
there are 2 of them
Yeah.
corresponding
Yeah.
to the axis.
Intermediate sphere to account for trepidation.
Yeah, and so they use it like a clock gear to
Yes,
express it.
And there are military
That's
spheres
why there is
which
the,
show this movement using gearings.
Yeah, And I was also intrigued by both of your presentation about, I mean, the process of scaling the cosmos also implies new kind of architecture, like for the observatory. And so you need to also find scale at the scale of a building, like for clocks, for telescope, and I don't know if you have, other example, like before, maybe in the antiquity or later, it's quite obvious, but before.
There is a long tradition. We don't know what Ptolemy used in the 2nd century and others, but with the Arabic tradition, they started to build observatory with specific purposes and programs of observation that last in the hope of the chief astronomer 30 years to complete the revolution of Saturn, but usually they were shorter because the patronage required quick results, and who put the money. But those observatories was usually about with the same instruments. You need a meridian line, you need a quadrant, you need a number of other armillary device, and this tradition goes up to Tycho Brahe in the 1580s, let's say a bit later, and also continue with the values in part with observatory were built in the top of his houses, but using particular astronomical instruments that are always the same with the improvements, of course, to make the better observations, and also improving the techniques of the observation, and combining hopefully the observation with the clocks. That was not at the beginning of the process of astronomy, observational astronomy.
I have a very short question for Günther.
Yeah.
That is, you said that Weigel can be considered as precursors of today's planetarium, some of his globes. And I wonder if you were also thinking about his heraldic celestial globes, where he...
No, I wasn't thinking of Weigel's so-called heraldic globes. These were quite small items. That is, whether they were typed on, well, to be put on the table. His giant pancosmos was a huge sphere of about, well, like the Gotthard globe of about 3 meters diameter. But, well, from the contemporary descriptions, it can be, well, qualified as a Baroque theater. It obviously had various show effects. Even the eruption of volcanoes could be simulated inside. But rather flowery description. One can hardly imagine, and also atmospheric phenomena like snowfall and rain could be demonstrated inside the sphere. I have no idea how this worked out.
I was asking because, you know, you could put, even in the smaller globes, a candle inside. There were some little holes to stimulate the stars, and so there is this spectacular component, this quest for spectacular elements. But, okay, thanks.
Perhaps I should mention in addition, the original Gotthard globe is only partly, or rest is still extant. It had been transferred to Russia in the 18th century as a present to Tsar Peter the Great, but it was damaged by fire in the 18th century and reconstructed by Mikhail Lomonosov. But the basic structure of some parts of the movement and also the ring construction and so on is still original. The only original part of the surface is the hedge with the coat of arms of Gotthard. This is still, well, this has survived this catastrophic fire in St. Petersburg.
Okay, thank you very much. So. next session that I'm going to chair, and which is entitled From Late Modernity to the Contemporary Era. So we're going to move forward within the chronological frame that Florian outlined this morning. This session will explore how the progress in science and technologies during the 18th and 19th century have extended the observation and the investigation of the cosmos, have extended the scale and consequently the scaling practices, following an expansion of the world, both in space and time, as we were saying yesterday. Also, this scientific advancement lead to an unprecedented dissemination of science, flourishing of the so-called popular science. So we will start to have a look at these new practices with the communication of Ilaria Ampollini. Ilaria, you can come. Ilaria is a tenure-track assistant professor of the history of science at the University of Ferrara in Italy. Previously, she was a member of the ERC Advanced Grant in Iconology, History, Theory, and Practices of Environmental Images with Professor Andrea Pinotti at the University of Milan. Her research focuses on the material and visual history of the popularization and education of science. Thanks to the LabEx Aztec IHMC Paris, she has worked extensively with understudied primary sources such as science-themed educational board and card games from the 17th to the 19th century. Her articles have been published in international journals such as Public Understanding of Science, Nuncius, Centaurus, Archives Internationales d'Histoire des Sciences, and Early Popular Visual Culture. Her first monograph investigated an essay published in 1773 by French astronomer Lalande, in which he analyzed the probability of an impact between comets and the Earth. And she's currently writing a second monograph investigating the use of immersive techniques in disseminating scientific knowledge between 1650 and 1900.
Yes,
Please,
it's me.
Ilaria.
Okay. So thank you for the invitation, and I'm really happy to be here. And so today I'm gonna talk about being immersed in the cosmos, which is a sort of contradictory because we are already immersed in the cosmos. But the point is to get immersed in the cosmos in a way that we can be able to understand it, to feel it, to sense it, and sometimes to manipulate it. So I try to give an overview about different representations and models of celestial and terrestrial globes, from the pocket ones, which were very popular during the 18th century, to the giant ones, like the Gotthard globes, but actually the walking globes became very popular during the 19th century, and particularly in France and England. So these are the themes that I would like to treat today. And the first point is what is immersion and what are the types of immersive techniques. This point is useful to me because it gives you an idea how the representations of celestial and terrestrial globes fit into a wider project of research, which is a project of research about types of immersive techniques. So, what is immersion? We have many ways to define it. I've been working on immersion because I was a member of this ERC project that dealt with virtual reality and environmental images. And I was supposed to be the historian of science in the group. So the idea is to see how the concept of immersion has changed over the centuries and in relation to the circulation of scientific knowledge. Some historians, some art historians and media archaeologists define immersion as it follows. So Griffiths defines immersion as the sensation of entering a space that immediately identifies itself as somehow separate from the world, allowing the spectator to move freely around the viewing space. And I think you are already noticing the connection to the walking globes. And Grau characterizes immersion as a stimulating process, mentally absorbing, which produces an emotional involvement in what is happening. Or, Soyer et al. Talk of dispositifs de simulation du monde, and they say that the observator, the visitor, the experiencer gets to have an experience of being immersed in another space-time reality. So this concept of immersion can be used, I argue, also in relation to the circulation of scientific knowledge. And I want to demonstrate that immersive techniques were crucial for the popularization of science and the circulation of knowledge since the very early modern age. Well, not very early, the early modern age. And my point of departure was this quotation from Cosmos by von Humboldt that all you know very well, I guess. And Humboldt, in the middle of the 19th century, put the accent of the importance of the panoramas, these 360 degrees painting which surrounded the spectator, the observator, invented in the end of the 18th century in Edinburgh by Robert Barker. And Humboldt pointed out the importance of these panoramas in the circulation, in the communication, in the popularization of the study of nature. For Humboldt, in fact, panoramas should have not only shown cities, like it was usual, but they should have privileged natural sceneries. Because they were perfect, he wrote, to communicate what we know about nature and the interconnection that characterizes nature and the world as a whole, and the relationship between the world and the cosmos and people, with the man as a part of the whole nature. Just very, very, very briefly, and sorry for that, but what I mean with the term immersive techniques between the 17th to the 19th centuries are these types of immersive techniques. I'm sorry that there's some problem going on with the, but anyway, with the words, but doesn't matter. So what I argue is that we can classify these techniques in these three categories. And the first one are the literary techniques. And here I build on Chapin and Schaffer's work about the modus witness, but particularly about the virtual witness. So the point is that literary rhetorical techniques were used in early modern England to make the readers feel as they were present during the experiments that Boyle was performing at the Royal Society, even if this was not possible, because the experiments were performed in front of a reduced public. Then you can talk of immersive techniques also in relation to optical devices. Like here you have a wonderful example of a book-guised camera obscura. So you could get to immerse yourself in the world as reflected within this portable device. And curiosity, one of the first models of portable cameras obscura was imagined by Robert Hooke, who stated that it was the perfect device for explorers to take notes of their exploration within unknown places. And then you have the third type of immersive techniques, which are the multimedia techniques, including 360 degrees environments, like the giant globes. And this is the celestial globe from the Paris World Exhibition, which is like the arrival point, the golden age of giant globes, of giant globes. And so if with literary techniques, you basically use words, and so you need sight to read and imagination to recreate in your mind the experiment or the unknown countries which have been described by explorer, or the aerial view of the Earth seen from the hot air balloon, for instance. With optical devices, you use both sight and touch because you need to manipulate them. And with multimedia techniques, so with these immersive environments, it is the whole body being immersed and all the senses being involved. So I don't have time, but the idea is that this different type of involvement build on a different conception of knowledge. So what does it mean to know the world, to know nature, to enter in a relationship with the world? This is like an assumption that stands at the origin of the developments of these different techniques. So why immersion and manipulation? Because you may say they are actually really different, yes. Even if the media archaeologist Erkki Utamo has pointed out that, building on Bachelard and Stewart, that miniaturization is the counterpart of magnification. In a complex cultural play with scale and transforming optics, things that are kept in the pocket or in a purse and manipulated with one finger are at the other extreme from huge spectacles. They are tactile, familiar, and proto-interactive, whereas public panoramas and dioramas overwhelm the visitors by enveloping them in untouchable, wrap-around surroundings. So, the first things I want to show you about scaling the cosmos are these wonderful pocket globes. And apparently, the first pocket globe that was published in London, in England, was published by Joseph Moxon. Maybe someone of you know him because he was a very famous publisher. He was a friend of Hooke and Boyle, and he published many mathematical textbooks, and he was the first tradesman to become a member of the Royal Society, the first elected member as a tradesman. And he also published, that's how I met him first, he also published educational card deck. About, for instance, mechanics, geometry, astronomy, and so on. And he also published the first pocket globes which were introduced on the English market. And then you have another example of the pocket globe. This is from the end of the 18th century. So here what you have the Earth depicted on the interior convex globe, and then you have the celestial vault depicted on a concave surface, which is the external globe that encloses the Earth. What were they used for? Because Moxon is very clear about it. He says, well, naturally, you cannot, it's obvious that you cannot use them to measure, for instance, or to gain any detailed knowledge about the Earth and the sky, but they can give you an idea of how the Earth is made, where the countries are, and where constellations in the sky are, and which constellations are visible. But there's another aspect which Catherine Parker has underlined, that is, with these pocket globes, you literally had the world at your hand, and you were able to manipulate it. You could keep them with you and then show them to demonstrate your knowledge of geography or astronomy, or if not your knowledge, your interest, to demonstrate that you were a gentleman. For instance, a gentleman deserving to take part at Royal Society experiments and meeting. There's one other aspect. They were far less expensive of the bigger ones, and also they come as one item solo, because you bought the terrestrial globe and the celestial concave globe together, whereas the bigger ones you had to buy two different globes, so they were much more expensive. They were portable, and they were constantly updated with the most famous voyages of the most famous explorers. For instance, here So it was really a way to demonstrate that you were engaged with the exploration of the globe, with the greatness of the British Empire, and with the relevance of astronomical and geographical knowledge in your everyday life. But then we have something more, because during the 19th century, astronomy was often taught at home, particularly to girls, like also educational board games very well demonstrate. And one of the assumptions of 19th century English, in this case English education, was that it was important to learn by amusement and by touching, by manipulating. It was an assumption that was promoted, that had been promoted by Locke and then by Comenius, and that was very much followed by female teachers, female teachers in private schools, or figures involved in domestic education. So, for instance, you didn't only have a pocket globe, but you have a globe that could be dissected, constructed, and reconstructed. So the idea is that you owned the world and the sky, because this is a couple of globes, so you have the celestial sphere and the terrestrial globe, but you were also able to destroy and rebuild it. Very typical of the early 19th century British Empire. And then another type is the miniaturization of the globe, both terrestrial and celestial, to construct globes in which you can dissolve yourself, in which you can sort of disappear. And these are the origins. So besides the gutter globe, we have later on, during the 18th century, these two interesting examples. One example, I found out this example in an article written by Charlotte Big and Vanut. So the first example is what we can call a human orrery, or a living orrery. The idea exposed in this text by John Rowland, An Easy Introduction to Mechanics, Geometry, and Astronomy, was that to understand the movements of the planets and the movements of the Earth, schoolboys had to perform the planets. No, due. Perché qua c'è scritto 22? Qua c'è scritto, giuro, c'è scritto 22. Però va bene, no, ok, va bene, vado. Scusate, no, stavo a questo e quindi ero molto, molto zen, ok. The idea is that you had to perform the movement of the planets. And so, where's immersion here? Well, the classroom is transformed in an immersive room by the movements of the schoolboys performing, acting as they were planets. And another example came from the first panorama of Edinburgh, painted by Barker, the inventor of the panorama. We don't have any other details about it because it's pretty much unknown. But here you can see, I mean, I'm not sure you can. planetary walk. So apparently, in Edinburgh, at the end of the 18th century, you could go for a walk among the solar system. Okay. So during these 2 or 3 minutes, I'm giving you some other examples very quickly of immersive devices. So the georama is, as Bess puts it, when the Earth turns into the sky, because in this first version, which was built in Paris in 1825, the Earth's surface was painted on the concave surface of this giant globe, which was around 12 meters of diameter. And the idea was that you could enter into the globe and look around and have at a glance an idea of what the Earth looked like. Then you also had the same idea in the Wise Great Globe from 1851 London. So you entered the globe, you look around, and you had an idea of the Earth at a glance. And then you have Reclus, who wanted to build a georama, and he said things like truth in scales. Therefore, it is that we must use globes instead of maps as frequently as possible. There is only one way to represent truly the surface of the Earth. Curves are to be translated in curves. Reclus was a geographer, and he was convinced that the maps were unuseful because they didn't give a precise idea of how the Earth looked like. But also, he did not agree with the Wise globe or Denglard globes because they used the concave surface. So for Reclus, the point was to have a terrestrial globe and to see it from the outside. And then the last one, but I have no time. But this is the ending point of all these immersive representation, miniaturized and immersive representation of the cosmos, which is the Cosmorama, which was built in Paris at the end of the 19th century, 1900. And it went through different projects. This one was a project from the phase that involved Flammarion 2, and the idea was to have also many dioramas and panoramas around, and then in the end it was built like that. So you had the celestial globe, and then you entered. Spectators were supposed to stand up within the Earth. So there was I finished. There was a smaller globe inside which represented the Earth, and you were supposed to stand there and look at the movement of the planets and celestial bodies from the Earth. And yeah, I finished.
Thank you. Okay, so let's go on with our next speaker, who is Charlotte Big. Charlotte is an historian of science at the French CNRS Centre Alexandre Coiré. She has published widely on the history of scientific instrumentation and visual cultures, in particular connected with modern astronomy and astrophysics. She has recently co-edited with Elsa Desmet and Kurt Van Houte a volume entitled Voir sans limite, sciences techniques et esthétique des origines, with Mimesis in 2025. She also works closely with curators of scientific collections and science museums, currently acting as one of the 9 curators in charge of the complete renovation of the Palais de la Découverte's museography. And her communication today is entitled Narrative of Cosmic Scaling and Their Alternatives in the Observatory Science since the 19th Century.
Thank you so much for the invitation, Madalena and Florian, and the Museo Galileo, which hosts many scales and many models, and is just the perfect place, I think, to talk about these topics. As Madalena mentioned, I will be using some of the thoughts that were published in this little volume that came out a few months ago, and also some of the work that has gone into forthcoming book, is that better? Called Imaging the Universe, A History of Astronomy and Photography, which was an attempt to, is it, okay? Is it better? Is that good? Can you hear me? I can hear myself. Yeah, so I will offer a few very tentative thoughts about scaling based on this book that has just come out a few months ago and another book that will appear soon called Imaging the Universe, A History of Astronomy and Photography, which is a bold attempt to combine the very technical histories of astrophotography that we have with the wonderful work that has been done in the last decades in the cultural history of astronomy and the cultural history of photography. But let me begin, and now I will have to switch. Hang on. And sorry, I didn't have time to set up. So ouais, il faut que je copie le lien du PowerPoint. Il faut que je l'ouvre sans le... Il faut fermer le PowerPoint. Ouais, ça doit être ça. So we're going to fast forward compared to Flammarion and globes, and we need the audio. Yeah?
All the radio messages that have been swapped. Nature doesn't do things in ones and twos. She's not mean. There are millions of planets, millions of stars and millions of galaxies, and very likely up there, millions of other different kinds of intelligent creature. If you think of the pygmies in an African forest, they are quite unaware of all the radio messages that have been swapped from one place on the earth to another. And I think we ourselves, in a larger scale context, are unaware of all the messages that have been sent even within our own galaxy. This is my suspicion. And I think our big problem in the future is to get ourselves into that galactic telephone directory.
Is man unique? Is he alone in the universe? Is he the Lord of creation fashioned by God in his own image and likeness? Or is the universe populated by countless millions of creatures incredibly more intelligent than man? Tonight, in our search for an answer to these questions, we look beyond our planet Earth, beyond our immediate neighbor, the Moon, beyond our entire solar system, to the further points of our galaxy, and on beyond the billions of trillions of other stars that abound in the infinity of space. Since the dawn of history, man has looked up at the night sky and wondered if intelligent life might exist on other worlds besides his own. This is not a science fiction program, but one in which scientists speculate and state their case seriously. Last April, the Russians announced that later this year, they'll start searching for radio messages from intelligent civilizations in outer space. A leading American astronomer who's played a major role in studying the possibility of intelligent life existing elsewhere in the universe is Dr. Carl Sagan. Dr. Sagan is a staff member of the Smithsonian Astrophysical Observatory and assistant professor of astronomy at Harvard University.
I and a few of my colleagues have spent a fair amount of time trying to find some evidence for intelligent life on Earth. By and large, we've been unsuccessful. Let me explain. Here are some photographs of the planet Earth taken by the American meteorological satellite ATS-1. The white stuff is clouds. The dark stuff is the surface of the Earth, in this case the Pacific Ocean. And as you see, there's no sign of life. Now, here's a photograph of the British Isles, and you can see this is a fairly rare photograph, rare because the British Isles are largely cloud-free. Now, prolonged scrutiny of this photograph reveals no sign of life. This is a photograph taken at 1 kilometer resolution. That is to say that things smaller than a kilometer would not possibly show up in this picture. Here's a photograph at the same resolution of France. Somewhere in this picture, I've forgotten just where, is Paris. Paris doesn't show up because there's nothing about Paris that calls it to our attention. You can't see Paris at this sort of resolution. Well, we've looked at several thousands of photographs with this sort of resolution, and we've come to the conclusion that at kilometer resolution, there's no sign of life on Earth, intelligent or otherwise. To get a good sign of intelligent life on Earth, we have to get pictures of improved resolution. Now, here's a rare photograph of the Earth at a resolution of about 1/10 of a kilometer. It's the only one of several thousands which shows with any reasonable degree of certainty, intelligent life on the Earth. I call your attention to this remarkable array of quite straight and parallel, and here we have at right angles to them crossing straight lines. Now, what can this possibly be? I think even if you don't have an immediate feeling as to what it is, it's clearly biological and not geological, and you'd be right. This is a photograph taken near Cochrane, Ontario in Canada. This is lumber country. The loggers have cut parallel swaths through the forest, and then the snow fell, heightening the contrast. But this is an exceedingly rare photograph, and to get really good signs of life on Earth, we would have to improve the resolution by another factor of 10 or 100.
Okay, so we can stop here, and I will try to elaborate. So we've moved forward to post-war scales, and we've had here Fred Hoyle and Carl Sagan, some of the most prominent astronomers, popularizers, but also science fiction writers of their generations, to tell us more about this particular idea of scale in the post-war decades. In the same program, Carl Sagan references Keith Book's book, which was the inspiration for another film that became very famous called Powers of 10, which you all know, and I won't have time to show it to you. So Keith Book's book is 1957, and there are two versions of Powers of 10 by Charles and Ray Eames, 1968 and 1977. Initially, it's a book about maths, about powers of 10, but in fact, it's also about scales and about zooming. And so just to remind you, there is a continuous zoom from a picnicking couple and into outer space, and then coming back down again into the hand of the picnicking man. The film takes us to the 24th exposure and back down again, this time zooming into the hand of the man. And what I'm interested in here is really how scaling comes to be. What are the parameters for different kinds of thinking about scaling come about? What are the technological parameters, the conceptual parameters, the material parameters for different kinds of scaling? Now, the post-war decades were also the beginnings of work on nanotechnology. Perhaps you will have in mind Richard Feynman's famous speech of 1959. There is plenty of room at the bottom. And then the work in the 1980s and 90s that led to the development of electron microscopes. Interestingly, they're called microscopes. They're not optical in any way, really. And what I will just hint at here is the ways in which the film, the Powers of 10 film, is produced for IBM. The nano work is produced. One of the first images to prove the ability not only to see single atoms, but also to move single atoms, is for moving them into the logo of IBM, and that is not a surprise. Carl Sagan spoke about... Yes, Carl Sagan spoke about the need to improve resolution as being the main challenge. And this is a language that you will still see today. So, is this launching? Oh, yes, there we go. So this is a little video offered by NASA that helps us to understand the difference between the Space Telescope Hubble, launched in 1990, and the Space Telescope Webb, launched in 2021, with the same region of the universe captured, and is being shown as a progress in resolution. So the metaphor of the zoom has remained powerful. James Webb is promising ever better images of the universe, even better than Hubble, that gave us incredible new insights from its launch in 1990. And this, of course, for those of you early modernists, may be reminiscent of a very famous text by Blaise Pascal, where he writes, and this is, of course, a very condensed version. Let man contemplate the whole realm of nature in her full and exalted majesty, and turn his eyes from the low objects which hew him around. Let him observe that brilliant light, set like an eternal lamp to illuminate the universe. Let the earth appear to him a point in comparison with the vast circle described by the sun. And let him see with amazement that even this vast circle is itself but a fine point in regard to that described by the stars revolving in the firmament. And later, Pascal writes, what is a man in the infinite? But to show him another prodigy no less astonishing, let him examine the most delicate thing he knows. Let him take a mite, which in its minute body presents him with parts incomparably more minute, limbs with their joints, veins in the limbs, blood in the veins, humors in the blood, drops in the humor, vapors in the drops. Blaise Pascal is, of course, very much inspired by the development of the telescope and the microscope in the previous years, as we've heard earlier today, and therefore provides a sort of echo to later considerations about the improvement of resolution and instruments as being the basis for this zooming metaphor. And yet, of course, the attitude is very different, because here Pascal is very much underlining the humility of man, the smallness of man in the universe, whereas through films like The Powers of 10, the power of man is emphasized, and the power through technology, through human-made technology, to know and perhaps also to control the universe. And it is worth pointing out that the Powers of 10 films were very much prepared under the advice of Philip Morrison. Philip Morrison, I think, does the voiceover of the 77 version. He was a physicist involved in the Manhattan Project to build the atomic bomb, and spent many years after the war promoting the peaceful uses of technology. And we see here also that IBM is So what I'm interested here is how scaling connects with technology, visuality, and the broader infrastructures of technoscience. And in thinking about, in particular, the politics of scaling, and I won't go into this very much, we can rely, of course, on a lot of very interesting work done by geographers in the last decades. And then I will only quote a geographer, an anthropologist called Neil Smith, who suggested in 2012 in an article on spatialized politics that scalar thinking, which in geography often connects the body, the home, the community, the urban scale, the region, the nation, and the global scale, that spatialized politics, he writes, is an historical artifact of the emergence of nation states in the decades around 1800, and the way in which it sought to organize, regulate, and control human activity. Geographical scale, he writes, is thus hierarchically produced as part of the social and cultural, economic and political landscape of contemporary capitalism and patriarchy. The point is precisely not to freeze a set of scales as building blocks for a spatialized politics, but for us, geographers, to understand the social and political purposes through and for which such freezing of scales is nonetheless accomplished. And so what I find interesting here, expanding beyond geography, is to think about how scales are made and how scales are communicated and what underlies them. And I will turn to Bruno Latour, who wrote a very little piece in an exhibition catalogue, very critical of powers of 10. And Bruno Latour writes, neither spatial nor temporal scales are continuous. Levels of reality do not fit together like Russian dolls. It cannot be said that the small or the short is to be found in the larger or the longer, in the sense that the larger and longer would contain them with simply less detail. So we go back to resolution. This metaphor comes from photographic optics, from zooming in with a so-called telescopic lens. Everything in this film, he writes, is both true and false. True because the images are each time what comes out of an instrument, a telescope, a satellite, a microscope, or a particle accelerator, not forgetting the camera that captures the lovers. But it's all wrong, because the positions given to these images are not at all plausible. Where would you have to stand to see the Earth from the galaxy? Where would you have to go first to observe the skin cells of our two picnickers? And how can we believe that we could go from microscope to particle accelerator in a matter of seconds? The space-time designed by the Eames film, which is wrongly described as educational, is a pleasant fantasy. If it makes perceptible what is called the scientific image of the world, it also reveals how unrealistic this image is. And Latour dreamed up a different exhibition, which he never really put together, opposing what he called the linear zooming in, the calamitous metaphor of the zoom, as he calls it on the left, to a different exhibition that would be based on another principle, the principle of connectivity, where the making of each different image in its specific place and lab and discipline would be documented. And in a sense, the space between the images would be restituted and not collapsed into a zoom. And he equated this telescopic zoom with a cinematographic, so I just showed you the stills, but a cinematographic attitude to scaling and to zooming. So if we were to adopt this attitude and look, for instance, at this view produced by James Webb of the Carina Nebula, released by NASA in 2022, we would want simultaneously to show what's behind it. We wanted to see here this artist impression of the Webb telescope. We could want to look at the ways in which the instruments, such as here the NIRCam, the near-infrared camera, a CCD kind of camera, the mirrors of Webb are installed in the machine. Of course, this is not completely radical because this is what NASA does. It also talks about the technology and how amazing it is. And so this is not such a radical move. All these images are very much part of the advertising. But you could also want to emphasize the immense project that James Webb has been, the 300 contributors worldwide, but a lot in the States and in Europe, and a bit in Japan. And as Robert Smith, a historian of astronomy who has studied Hubble to a great extent, and also the making of Webb, These are some of the largest mega science projects, as he called them. This cost 11 billion. So if you wanted to zoom out again and think about the Carina Nebula images and the Space Telescope images, you might want to think of it as part or continuation of what has been called big science. Big science in the decades during and after the World War describes, as you know, a new way of doing research involving vast amount of funding and associating state, industry, and military partners. So big science has been thought about mostly with relation to nuclear issues, but it's also very much central in the development of space program and the Apollo program and the space telescopes. So the beautiful images of Webb space telescopes are also product of this nexus of military-industrial state research inaugurating during the World War and the Cold War, and underline very much Carl Sagan's presentation of resolution through telescopic satellite observation. And the broader context of this, of course, is an effort to understand but also to control the environment. So the Pentagon in 1961 declared in a paper that the environment in which the Army, the Navy, the Air Force, and Marine Corps will operate encompasses the entire globe and extends from the depth of the ocean to the far reaches of interplanetary space. These are connected enterprises. This is, as you know, how we also get a lot of the data that enabled us to measure climate change and was also central today for studies of the origins of life. Now, if we go back a little bit in history and think about the genealogy of those kinds of enterprises, I would argue that they originate in the observatory and the observatory sciences, and a major turn at the end of the 19th century with a new set of instruments, among which the spectroscope is fundamental in the development of the techniques of spectral analysis by Bunsen and Kirchhoff in 1859 and later on, that enabled a new way of connecting astronomy and earthly concerns. The possibility of putting on the same map spectra from the laboratory and spectra from the stars and up to Sirius. This, as much as Humboldt's great idea of the cosmos and the interconnected study of the different parts of the world, is at the heart of the development of the new kind of observatory sciences that appear in the late 19th century and that are encapsulated here, but also in many other places, in the ensemble of observatories that are built in Potsdam outside of Berlin by the new Prussian state and reunified Germany after 1871. And you have here institutional, instrumental materialization of this project where the Astrophysical Observatory is built outside of town, just next to the Geodetic Institute and to the Magnetic Meteorological Institute. This, in a way, is the big science of the late 19th century. And this, in a way, is one of the bases for the kinds of scaling that we will see emerging later on. This is science. This is also at the service of the techno-scientific enterprises of the Prussian state. And Carl Zeiss Jena, the optical instrument-making firm, is providing all these instruments with optical devices, as it is also providing the armies with telescopes and also microscopes for a whole bunch of other enterprises. This is part of a general ambition, and here I'm just talking about Germany, to develop also colonial ambitions. Here is the map of the visibility of the transit of Venus of 1874, for which the first time the German astronomers participated. They sent 5 expeditions in very much an attempt to impose themselves politically and scientifically on the world stage. And the popular science version of that is the creation of a popular observatory in Berlin called the Urania, and a journal called Himmel and Erde, which very much encapsulates this new way of articulating the earth and the sky. And the Urania has a wonderful scientific theater in which you can travel. Now, of course, space travel and going to the moon has been going on for a long time, but this, I would argue, takes on a new flavor. the ways in which the reconfiguration of the observatory sciences in the late 19th century are intricated with narratives of conquest is made particularly clear, I think, in fiction. And for instance, in this preface to War of the Worlds by H.G. Wells, who writes, "And before we judge them too harshly, we must remember, so them the aliens, what ruthless and utter destruction our own species has wrought, not only on animals like the vanished bison and the dodo, but also on their inferior races. The Tasmanians, despite their human likeness, were completely wiped out in 50 years by a war of extermination led by European immigrants. Are we such apostles of mercy that we would complain if the Martians waged war in the same spirit?" And here, channeling the historian of art Elizabeth Kessler, at the time in the late 19th century, and since when the Hubble images, the first Hubble images, like the Pillars of Creation here, were released, the uncanny similarity between visual narratives of the conquest, both geographical and technological, of the great American West, were compared with the new kinds of aesthetics that Hubble, with its CCD imaging and software working of the data, managed to produce. And I will just finish in an opening for the next talk, because we will be hearing from Thomas Moser about the planetarium, the ways in which the planetarium, so a product of Carl Zeiss, that is here shown in the 1923 experimental device set up on the Jena factory, the planetarium in a way encapsulates these tensions and these contradictions. The planetarium is the later avatar of globes like the Gotthold globe. It comes out of a tradition of great mechanical globes and orreries, but it's also optical. Very quickly, people will start putting cameras, film cameras in, because in a way, the planetarium arrives in the age of astrophysics, in which positional astronomy is really good, but you can't just do positional astronomy in the 1920s and since, and so you need to integrate the astrophysical dimension. And at the same time, the planetarium itself is from very early on the object of criticism from people like Walter Benjamin, who criticize the technologically mediated, the product of technological industrialization as a way of substituting for the experience of the night sky. And I will leave you with those thoughts. There we go.
Thank you very much, Charlotte. I will invite Ilaria to join us for the discussion. And I will start by answering you if you have any questions. Okay, then I'll start and open the discussion on this contemporary period. Thank you very much for your talks. I think that we've clearly seen with previous talks, and especially Günther's one, how actually some immersive devices, the will to create a spectacle of the cosmos already existed. But listening to you both in the 19th century, I have the feeling that scaling, the act of scaling, also becomes an act of power. And this component is stronger. Charlotte, you talked about creating narratives of conquest. And I think that in the 19th century, this creation of narrative of conquest through science is also possible thanks to the popularization of science and also the broader circulation of these devices that one can manipulate, hold in their house, hold in their pocket. Then I have questions on pocket globes, but maybe I'll come to it later. So I just want to ask you both, what do you think about this?
Yeah, sure. I think that the dynamic of Charlotte, the dynamic of control is very. I mean, is so much there, and if you think about what it did mean to be able to manipulate a pocket globe, you already have the dimension of control, of controlling the world, as I said, but with giant globes, the situation changed, and it was like it went to a next level, because there you have the control of how knowledge is popularized but also perceived by the public. What I mean is that until you have a pocket globe or a table globe, the use of these devices was a private use, or at maximum an educational one in private schools or schools in general. But then you have these giant, spectacular globes where you try to control how the public use the device you have projected. So yeah, I think it's really a matter of control, and also it emerges from the debates about what was the best globe to communicate geographical and astronomical notions, like for instance Reclus or de Langlade or Wilde, and when you talk of giant walking globes, actually you talk of very different types of globes and very different ideas of what geographical and astronomical knowledge is, and how it has to be conveyed to the audience.
Thank you, Madalena. I think you could probably tell similar stories about early modern scaling objects and stories have been told about how those kinds of enterprises serve, navigational purposes, and how they are very much embedded, and we've seen that today in courtly cultures, and scientists need to find their funding. So the issue of power, I don't think, is particularly specific to the modern period. It expresses itself differently. Perhaps an interesting question would be to ask, to what extent are models a way of mastering and controlling something more generally, in an epistemological sense? Is having the globe in your pocket somehow, grasping it literally and conceptually?
Thank you so much. It's just that I felt while listening to you that the issue of controlling in the modern period, it's like more visible on a broader social scale. But maybe we can discuss this later. Do you have any questions? Yes.
Hello, thank you very much. I have a question for Ilaria on the diorama. First, does any museum keep some part of those diorama, or are they all destroyed? And also, I would like to know if have some example of diorama showing the inside of Earth, like as Jules Verne did. Thank you.
No, so I think they all got destroyed. I actually have no clue about some dioramas surviving, and even the Cosmorama is not there anymore. It was just next to the Tour Eiffel, so we would see it, but no, it's not there anymore. Nice question, and no, I haven't met any examples of dioramas showing the interior of the Earth, but Maddalena has written an article explaining and describing the immersive representations that was at the same Paris exhibition of the subterranean world. So that's the
great. Thank you.
That's the most similar thing. It was really inspiring, her work, actually, because because the Paris exhibition is like the apogee of immersive representations of the world, the cosmos, and the subterranean world, and everything was there. So.
Thanks.
Other questions?
What strikes me most is that manipulation of space and time has always been there. The celestial globes contain the path, the trajectory of ancient comets. You have shown on the pocket globes the trajectory of the expeditions, the discoveries. So it seems an invariant during the time.
Yes, it's probably immersion is probably a more strict definition because it assumes that you are transported and wrapped up in another dimension. But I get what you mean, and yes, you're right, but it's slightly different. We can talk.
I mean, it's certainly true for the planetarium that enables you to travel in space and in time, forward and backward. And I love the analogy with the similar kind of thinking in Renaissance painting, how because astronomy is like this, you find ways to convey that, which are very inventive and original.
Other questions? In this case, I think that it's the coffee. Thank you again. Okay, so now we will resume, but before going on, very important information about the dinner. The dinner will be at 8 p.m. at a restaurant called Trattoria da Benvenuto, which is very close from the museum. It's like 1 or 2 minutes walking, but if you need further instructions, ask me. Okay. Da Benvenuto. Exactly. Do you approve? No, nothing. Okay. So this session will conclude our overview of scaling practices by analyzing the 20th and the 21st century and what we have defined as visual displays that may be considered indeed as scaling practices. One is cinema, the other one is exhibition and museum displays. So I will invite our first speaker, Thomas Moser. Thomas holds the position of Universitätsassistent, which is assistant professor, I think, at the Vienna University of Technology, and a PhD in art history from the Ludwig Maximilian University in Munich. He studied art history, philosophies, and architecture in Munich, Paris, London, and Vienna, and had fellowships and guest residencies at the Biblioteca Hertziana in Rome in 2023, the Getty Research Institute in Los Angeles in 2022, and the Warburg Institute in London in 2021. The DFG Research Group, Immaginaria of Force at the University of Hamburg in 2020, and the Centre Allemand d'Histoire de l'Art in Paris. Previously was an associated doctoral candidate of the research group Pre-Modern Objects and Archaeology of Experience at the LMU Munich. Curatorial and scientific coordination of exhibitions. He also had curatorial and scientific activities of exhibitions at the Hessian State Museum in Wiesbaden, the Vienna University of Technology, and the Architekturnzentrum in Vienna. His research focuses on the art and architectural history of Europe and North America from the 19th century to the 21st century. Central areas of interest include the history of science and technology, gender studies, object studies, eco-sensitive art histories, photography and film studies, and post-decolonial futurologies. Thomas, please.
Hello. I hope you can hear me like this. Otherwise, let me know so you can understand everything. First of all, thank you very much for the warm welcome and the invitation. This is a rather new project for my second book project. Actually, and I'm super excited to present. This is actually the first time. It's a literal work in progress, and I'm super thankful for any constructive criticism on this. So, in the archives of the UNC Chapel Hill Libraries in North Carolina, there's a black and white photograph that shows Gemini 4 astronauts, Edward White and James McDivitt, inside a rather peculiar setup. The two young men sit beneath a wooden canopy, each holding a flashlight, while a small NASA logo is fixed on their side. Their faces are visible only because the picture was taken from a steep low angle. A bit of light falls on them through two narrow openings in the cramped capsule. Through these small portholes, the two spaceflight trainees appear to orient themselves inside a dome-shaped, geometrically gridded space. Above a column of bare electronics rises a metallic sphere lined with round glass panels, a curious mixture of carpentry and high-tech. This image documents how American astronauts from the Gemini, Apollo, Mercury, and later Skylab and Apollo-Soyuz programs were trained in celestial navigation starting around 1960. Almost all of them, including White and Devitt, received this training at the Moorhead Planetarium in North Carolina, built in 1949 as a state-of-the-art university planetarium. For the astronauts, the planetarium's director had developed an elaborate program with several exercises. First, trainees memorized the constellations defined by the International Astronomical Union simply to learn how to find their way in space. The highlight of the training then, which for Neil Armstrong, for instance, lasted about 130 hours, was an immersive simulation. Here again, immersive. As the photo suggests, the candidates sat in a rather uncomfortable mock-up of a space capsule from which they experienced a simulated flight path through tiny, awkward windows. Behind them, the projection apparatus recreated the matching animation of the surrounding cosmos on the inside of this dome. Through its enveloping darkness and sophisticated lighting system, the planetarium became the most powerful terrestrial stand-in for outer space. It was a place where the nation's space program met astronomical education, and where not only astronauts, but also ordinary citizens could feel like astronauts for a moment. In this period, planetariums became institutions where space travel could be both understood and, in a way, experienced. By the early 60s, there were already more than 200 planetariums across the United States, constituting a genuine mass phenomenon. The most famous, second oldest, and perhaps the, architecturally speaking, most spectacular among them was located high up in the Hollywood Hills. The story of the Griffith Observatory began with a testament of the wealthy businessman Griffith J. Griffith, between 1919 stipulated that 2 buildings should be erected on the land he had already donated to the city of Los Angeles back in the late 19th century, the site known today as Griffith Park. One of these 2 buildings was to be the stage for the Greek theater, the other a public observatory. With support from astronomers Walter Adams and George Hale, Griffith developed his initial ideas, which were later realized through designs by Russell Porter, Frederick Ashley, and the local architect John Austin. Since 1934, the central rotunda of the building has been decorated with wall and ceiling murals by artist Hugo Bellin. Each mural panel illustrates progress in one of several scientific and technological fields: astronomy, obviously, aviation, engineering, metallurgy, electricity, geology, biology, mathematics, and physics, all framed within the ecological setting of California. Stuart Leslie and Emily Margolis have argued that these murals present Southern California as the culmination point of a linear modernist narrative of scientific and technological advancement in the States. When one steps into the room, an octagonal floor plan opens up beneath a late symbolist ceiling painting that, in the tradition of early modern illusionism, reveals a crowded view of the heavens above. Around the spiral of clouds rising from the terrestrial landscape, mythological figures gather: a giant atlas bearing the celestial sphere, various gods, the moon, and at the very top the sculpted signs of the zodiac. This astrological sky is both supported by the scientific positivism below, and at the same time positioned both spatially and semantically in front of the true astronomical dome of the Samuel Orchin Planetarium right behind it. This deliberate juxtaposition intensified the visitor's experience. The main attraction, the immersive encounter with the cosmos inside the projection dome, stood in intentional contrast to the symbolic and painterly worlds that preceded it. Modern astronomy thus replaced the visual language of astrology. Technical light projections took the place of painting, diagrams and explanatory texts gave way to animated audiovisual spectacle. What had once been didactic display turned into an experience of sight and sound that had evolved dramatically since its invention. About 10 years earlier, as we already heard, in 1924, Carl Zeiss had built the first projection planetarium on the rooftop of his factory in Jena in Germany. He coined the telling term Sterntheater, literally star theater, which already captured the built-in tension between science and entertainment. Using a film projector, stars and occasionally planets were cast onto the inside of a domed room. In the early 60s then, the A3P projector, developed by the American engineer Armand Spitz, set entirely new standards in this field and quickly became the world's best-selling model. While it was somewhat less precise than the European size systems, it was lighter, cheaper, and capable of representing more complex astronomical phenomena. The A3P allowed for the motorized movement of the sun, moon, and planets, and it could project up to 1,500 stars simultaneously. In an article on the precursors of the planetarium, the science writer Willy Lai explained in 1965 that by the end of the war, it had finally become technically possible to simulate what it would be like to orbit Earth like a satellite and to travel from Earth to the moon and back. Until the 50s, most planetariums had avoided showing Earth itself since their goal was to reproduce the terrestrial perspective into space. This geocentric viewpoint was soon abandoned with the rise of the space age as planetariums began to simulate satellite motion and lunar travel several years before such missions became reality. Interestingly, though, Lai also noted that many planetariums displayed historical orreries for comparison. These mechanical models, as you all know, showed the planets revolving around a fixed sun, drawing attention to the viewer's own position within the act of observation. In this somewhat comparative way, visitors learned to distinguish between different modes of astronomical representation and also to reflect on how each of them mediated knowledge differently. Planetariums then were not merely places where knowledge about the structure of the cosmos was transmitted. There were also places where knowledge about how the cosmos was represented and experienced could be explored. The very mediality of the planetarium was famously criticized by Walter Benjamin in his short aphorism Zum Planetarium, on the planetarium, where he limited its emphasis on vision and the loss of a collective, static experience of the cosmos that ancient stargazing once provided. Benjamin, however, probably underestimated the power of music and sound in these environments, as well as the increasingly spectacular animations that characterize post-war planetarium shows. He also overlooked the complex relationship between natural celestial phenomena and their technological projection. His colleague Hans Blumberg wrote about this far more lucidly and with much more sympathy for the planetarium in '75, and I quote. You see on the right-hand side the German original, and I translated it into English as good as I could. The absence of the sky's appearance under the conditions of the modern city and the weakening of the very notion of reality under the conditions of modern science produced the medium in which the technically simulated starry sky could become a museum-like present. This prepared and mediated experience is unique compared to other preservations of nature in aquariums, zoos, and botanical gardens, where nature appears lonely and diminished in isolated specimens, whereas the starry sky, through technical simulation, seems rather amplified in its abstraction, end of quote. In other words, the planetarium compensates for the loss of the natural night sky by technically recreating it. Though the idea was born from the positivism of the interwar years, in the media installations that followed, scientific knowledge and aesthetic experience were soon productively intertwined. The human relationship to the cosmos, once direct and contemplative, became mediated but not impoverished. Quite the opposite, actually. In its musealized, artificial form, it took on, to borrow from Edmund Burke, a rather like sublime quality. Hans Christian von Hermann has fittingly described this intensified mediality of the planetarium as a form of, this is his term, hyperreal simulation. When the Griffith Observatory's foundation stone was laid, expectations were still shaped by the desire for faithful imitation. As one contemporary article put it, it would be, quote of this article to the, on the occasion of the opening of the observatory, difficult indeed to perceive any difference between the counterpart and the original, end of quote. This relationality, the comparison between projection and natural phenomenon, was at the heart of the fascination. The Griffith Observatory even offered several distinct ways of studying the universe side by side. As a media reproduction inside the planetarium, and as direct observation through the large telescope on its terrace. The author of this said article described the latter, the large telescope, as a celestial panorama. So from the very beginning, the observatory was conceived as a site of visual mediation, an educational institution devoted to training the eye in astronomical seeing. The article from the period explicitly listed the observatory alongside other academic institutions, such as the UCLA, the USC, the Huntington Library, and Caltech. By the late 50s, the observatory's first director, Desmond Alter, following Griffith's testamentary wish that it be free to the public, had established collaborations with numerous local schools offering guided tours to nearly 60,000 students every year. And its educational mission gained strong political momentum, obviously, during the space age. At the same time, the institution increasingly sought to enhance its entertainment value. From then on, the planetarium repeatedly faced the accusation that it was perhaps leaning a bit too far towards spectacle. And indeed, while the Griffith Observatory could not claim major scientific discoveries, it played a pioneering role in the realm of media spectacle. Notably, Desmond Alter, again, the observatory's first director, was an early believer in the coming age of spaceflight. As early as 1948, he staged an elaborate simulated journey to the moon titled A Trip to the Moon. Using custom-built projectors for special effects, including zooms and panoramic sequences, Oltre created the illusion both of a rocket launch and lunar landing, like in the late 40s already. In Los Angeles, the navigation of near-Earth space thus became another mode of representation, one that stood in direct juxtaposition to orreries, astrological ceiling paintings, hyperreal projections, and telescope-based observation. Yet Oltre's ambitious lunar simulation drew on a resource that no other planetarium could match: its proximity to Hollywood. Time and again, Oltre collaborated with artists, model builders, and writers from the film industry. Even the astronomer's monument outside the observatory had already involved George Stanley, the sculptor who famously designed the Oscar statuette. For the moon landing show inside the planetarium, Oltre turned to Leon Bayard de Volo, a model builder in the film industry and artistic director of the nearby Greek theater. De Volo constructed a plaster model of the Copernicus crater on the moon, which the observatory staff then enlarged. It was filmed through a window frame designed to resemble a spacecraft porthole and projected as part of the lunar landing sequence. So this is like film techniques. Through this contextualization of the projected field of vision, visitors no longer simply found themselves in outer space, but inside a spacecraft. Technical aspects of the installation faded into the background, giving way to the kind of embodied sense of immersion already familiar from the cinema. Oltre consistently sought strategies that would authenticate fiction. In '57, for example, he exhibited paintings from Cecily Bonestell, the naturalistic space artist who illustrated many of Wernher von Braun's publications. And as NASA prepared for its first manned spaceflight, it regularly sent exhibits to the observatory in LA, including models and mock-ups of the rockets, spacecraft, and orbiters being designed and built in Southern California to carry humans to the moon. Also, astronauts themselves were occasionally trained in this observatory, further validating the credibility of its displays. Within this gravitational field, astronomy, spaceflight, and Hollywood merged into a multifaceted experience of education, participation, and entertainment. Through its projection apparatus, film and planetarium were ontologically related as media, but in the Hollywood Hills, they also became spatially intertwined. The Griffith Observatory's space projections resonated with the many nearby cinemas in which the observatory itself repeatedly appeared on screen. Among its numerous cameos, Nicholas Ray's Rebel Without a Cause from 1955 gave the building its most iconic role, one it shared in a sense with James Dean. In the film, key scenes unfold inside and around the planetarium, where the teenage protagonists confront both cosmic and personal crises. The planetarium show, featuring a dramatic projection of a constellation of Taurus, mirrors their inner turmoil and foreshadows the film's tragic events. Merrill Schleyer has argued that the observatory functions both as a temporal framework for the story and as a simulation space for trauma, fear, and existential anxiety. Within the cinematic architecture, philosophy, society, geopolitics, and astronomy converge. The observatory's dome structure and temple-like form serve as, and I quote her, both timeless classical monument and substitute universe, end of quote, a setting that dramatizes the loneliness and fragility of human existence. In Rebel Without a Cause, LA's cosmic imagination folds back upon itself. The planetarium becomes a stage on which terrestrial conflict and celestial order are mirrored and entangled. From the very beginning, the Griffith Observatory has been designed to link two types of vision: the immersive view into outer space within its planetarium and a spectacular view from its terrace of the galactic cityscape of Los Angeles below. In Rebel Without a Cause, it functions much the same way, as a hinge between different spatial and symbolic registers. 1950s science fiction films made use of this site specificity as well. The observatory appeared in The Cosmic Man in 59, and in the finale of Phantom from Outer Space, 53, the nameless extraterrestrial returns quite literally to the very place from which it had come, the observatory in the Hollywood Hills. In these films, the Griffith Observatory itself became a portal to outer space. Rainer Banham famously described the futuristic facades of Googie architecture, the simulated space journeys of Disneyland, and the film sets of Hollywood studios as proof that Los Angeles as a whole was a what he called fantasy machine. The Griffith Observatory was a place where that machine could be experienced, and one that also acted within cinematic fantasies. Against this background, the current director of the observatory, Edwin Krupp, argued in 2001 already that the institution deserved its own star on the Hollywood Walk of Fame. In Hollywood, after all, film celebrities and celestial bodies overlap in language. Both are called stars, and astronomical metaphors, luminosity, gravity, orbit, are used in abundance to describe fame. Hollywood was not only a planet, but an entire universe, and in some ways a distorted reflection of the real one. When the Walk of Fame was created in the same year Sputnik was launched, it became a literal ground of intersection between astronomy, cinema, and urban spectacle. Today, with more than 2,700 stars, it has achieved galactic proportions. Not really, but you get the point. Its special quality emerges at night, when between the black terrazzo tiles and the inlaid stars light up in the glow of neon signs. Here, one could stroll through outer space on foot, while glancing from the star-shaped lights beneath one's feet to the Hollywood sign and the Griffith Observatory above, and finally, to the night sky beyond. Thank you.
Thank you very much, Thomas. So I will ask Enguerrand to join us. So Enguerrand Lascolz is an art historian and museum curator, conservateur du patrimoine in the Museo in Marseille. His research are about theories of art and heritage during the 1930s. So it's within this frame that he became responsible for the permanent display at the Muséum Méditerranée, Invention et Représentation in 2024. He's also interested to the link between artistic creation and environmental issues. That's why and how he was a commissioner for the exhibition Lire le ciel sous les étoiles en Méditerranée, so reading the sky under the stars in the Mediterranean, which is now ongoing at the museum. And also he has been working on another exhibition that will open in 3 weeks, and the title is Clément Cogitoire, Ferdinandaire, l'île éphémère. And now Enguerrand is going to present us the exhibition Lire le ciel, for which also, as I told you yesterday, the Museo Galileo collaborated. So let's see how exhibiting and conceiving exhibition display can be an act of scaling.
We'll see. Thank you, Madalena, and thank you for the invitation and for this day that was very interesting. So I'm going to present you the exhibition Lire le ciel that opened at Museo, so in this museum in Marseille, in July. So the exhibition lasts 6 months, so it will close on January. And it's an exhibition that explores the history of astronomy and astrology in the Mediterranean, trying to make links between all the culture and of the Mediterranean, showing how astronomy and astrology was a common science for centuries, and that common sky was built that we still inherited today.
So it goes from antiquity to nowadays, so it's a big subject, with 350 works, most of them from the Museum collection, but also from the Louvre collection, which is a big lender for this exhibition, and of course from Galileo, Museo Galileo. So there are three main subjects that I wanted to talk about in this exhibition for this presentation. The first subject that is in all the exhibition is that, as I said, there is a common sky that was built throughout the centuries. And to do so, we presented objects from different civilizations of the Mediterranean, from different cultures and from different times, showing the links between all those cultures, so beginning in Mesopotamia in the third millennial before Christ, and going through Greco-Roman antiquity, but also to Arabic time in the Middle Age, sorry. And we really wanted to focus, sorry, I haven't told that it's an exhibition that I've curated with Juliette Besset, which is an art historian at Université de Lausanne. And with Juliette, we really wanted to show how this common sky was constructed throughout the years with those kind of examples. Sorry, I just realized that all my labels are in French, but I hope that you will, no problem. And there is one missing also for this globe. So we presented those kind of works. This little globe is quite interesting. It's the oldest sphere, known sphere, from probably from the 2nd century BC. It's actually in a private collection in Paris, and it comes from Turkey. And it shows most of the constellations that we still know today. There are only two on this globe that we don't know that are probably from the local culture in Turkey, but most of them are the ones that that were described by the Mesopotamian and given to the Greco-Roman world, and that we still use today. This globe on the middle is a globe from the 11th century, one of the oldest Arabic globe, with the one that we saw yesterday in the Museo Galileo. And it's from the BNF in Paris, and it shows also, as I said, all the constellation. We make a focus on this book, Livre des Étoiles Fixes, which is a very important book from the Middle Age that was written by an astronomer called Al-Sufi and was really spread all around the Mediterranean. And in this book, we show in the Ptolemaic heritage the constellation of the sky described with all the stars that compose them, with some of them that are specific to the Bedouin culture, but most of them are this heritage that is the subject of the exhibition. So this is the view of the first part of the exhibition. The scenography was made by the Parisian agency Nathalie Crinière, which is a famous agency in France doing for exhibitions, and she decided to create this, how do you say, dégradé? I don't know how to say dégradé, but sorry? Of color on showing the links between Earth and the sky. So that was a very nice view for the exhibition, idea for the exhibition. You see the very little globe that I've just talked about. It's really tiny, and we showed it with a cast of the Atlas furnace. We didn't ask for the Atlas furnace, but this is a plaster from the Louvre Museum from the 19th century, and you see in the middle the Arabic globe that I've just talked about. This is the view of the books from the Livre des Étoiles Fixes and the books from the Middle Age that are very important, showing this heritage that passed by all the culture of the Mediterranean from antiquity to modern period. With contemporary artwork, as you can see we tried to add contemporary artworks in all the exhibition, even though it's chronological. Here it's a work by, on the left, it's a work by a Moroccan artist called Mohsin Araki. He represented the constellation of the Livre des Étoiles Fixes in this 30 tablets, metal tablets. We advance in time, so in the Renaissance, here with a very nice globe from the Musée des Coins, and also with this astrological disc from the Museo Galileo. There is a text on it by Giorgio Strano in the catalog, if you want to read it. And also contemporary artwork, as I said, this work by Mohsin Araki, also a work by Clément Cogitor called Atlas. So he made a photography rethinking the myth of Atlas holding the sky on his back. So this view of the exhibition. The other subject that I wanted to talk about is our place in the cosmos. The exhibition is not on our place in the cosmos. It's really the main subject is this history of the constellation. But of course, we couldn't talk about the place we think we have in the cosmos. So in antiquity, we showed some work from diverse religions of the Mediterranean, polytheist and monotheist religions, that shows how the sky is a religious sky created by and designed by a divine force. We had the luck to show this, to present this amazing fresco from archaeological museum in Napoli, showing Apollo as a cosmocrator holding the sphere symbolizing the cosmos, with the two lines of the horizon and the ecliptic on it. So it's a very fascinating work, and we linked it with objects that comes from radically different cultures. Here, a work showing how the Egyptian in antiquity studied the night sky and thought that the night sky was like a sea where the planets and the stars were in boats and navigating in the sea. And in the biblical tradition, how God created and designed the night sky, the moon, the stars, the sun, and Adam and Eve. So this is the view of this exhibition, Of course, we talk about the geocentrical universe, and with a main focus on Ptolemy, who wrote in Alexandria the reference work on astronomy and astrology. We show this, I think, very interesting manuscript from the 10th century that is translated in Latin of the Aratos de Sol phenomena, and it's kept in a Bibliothèque des Annonciades in Boulogne-sur-Mer, so it's in the north of France. And in this book there is this very nice planetarium presenting a mixed model of the universe order, geo-heliocentric, because as you can see, depicts the planet Venus and Mercury orbiting the sun, while the others are shown orbiting the Earth in the middle of the planetarium. In this, so those books are presented right here on the right. You can see the phenomena in the middle. We evolve through time, and we evoke, of course, the scientific breakthrough of the 16th century with Copernicus, and the Earth that is not in the center of the cosmos, but actually revolved around the sun. And we wanted really to focus on this scientific revolution of heliocentrism in this room, as you can see, with scientific objects. Most of the objects from the Galileo Museum are in this vitrine, just on the left. We show, so there is an error, sorry for all my labels. Francesco Curti, it's the one in the middle, and Andrea Celarius, it's the one on the left. I wanted to focus on the Curti print. It shows Ptolemy's long-accepted geocentric model of the universe relegated to the ground, as you can see in the middle, while the theories of Copernicus and Tycho Brahe are waged on the scale in the middle. So this is the room where we present all those artwork from the modern era. We had the luck to present the Astronome by Vermeer. So it was the big thing of the exhibition. It's not presented now because we had it for 3 months, not for the 6 months of the exhibition, but it was a great news for Marseille and for Museo. And just linked to those two, so here is on the left is Luca Giordano from Musée de Chambéry, and it's from the 160, and Vermeer is from 68, so it was a nice presentation of how artists in the middle of the 17th century imagined astronomer. And really linked to those two portraits, we made a focus on Nicolas Fabrique-Peresque, who is a French astronomer from Aix-en-Provence, so really near Marseille, that observed the Jupiter's moon, right? I don't know in which year Galileo did the first observation of the... Yeah, 1610, and here it's 1611, and the two had a correspondence, and so it's really interesting to focus on that astronomer. Here it's an archive that is kept at Bibliothèque Ingambertine in Carpentras, showing every night, the Jupiter and the position of the 4 Medicean stars that he observed with those kind of lunettes that we show here. It's optical lenses and an object kept in museum, the Marseille Museum. And the third big subject of the exhibition, of course, it's the influence of the stars, and how we thought for a long time that stars had an influence on the microcosm, which is the big subject, because it's not the main subject of the exhibition, but when I do presentation and when we do visits, everybody talks only about that, the influence of the stars. So it's a big thing. So we explained that scientific observation are really linked astronomy and astrology for a long time, and this belief suggested that the stars that supposedly revolved around the Earth influenced societies, people, and living entities. Over the centuries, these diverse beliefs and understanding evolved and were reinterpreted as they moved through the different civilizations in Mesopotamia, Greece, Egypt, and later the Arab Muslim world. And according to certain beliefs, there are connections between macrocosm and microcosm, between heaven and earth, and it is the subject of those very beautiful treatises from the Middle Age that are kept at BNF in Paris, and that explain the influence of the planets on human behavior and their position in the zodiac constellation. So here you can see the balance. How do you say balance in English? Maybe it's not balance. Yeah, I just said it. Yeah, with Mercury and Venus, and just underneath Saturn, Mercury, I think, also the Sun, Mars, and the Moon. Here in the middle, you can see Saturn on the Capricornus, and those treatises explain that the position of the planets in the zodiac sign had an influence on people. and we showed them really close to those prints from the Renaissance, showing the same thing, but in a very different style, but it's the same subject, showing the planets with a human form, linked with the zodiac constellation, and showing their influence on people on Earth. We talked about astrology. I don't know why I speak in the past. The exhibition is still open in museum. So we talk about astrology, of course, with this amazing print by Dürer that is kept at Musée des Beaux-Arts de Caen. All the prints that I've showed you, most of the prints that I've showed you are from the Musée des Beaux-Arts de Caen. But we try to focus also on popular culture and on the influence of the star in popular culture, because Museum is it's a museum that opened 12 years ago in Marseille, but it kept the collection of Musée des Arts et Traditions Populaires, which was a folk art museum in Paris during the 20th century. So we made lots of focus showing how popular culture, mainly in Europe, kept some beliefs and some knowledge of the antiquity, even though science disapprove it. So here it's we have lots of books from shepherds books that are calendars that are supposedly written by shepherds, and the shepherds explain the cycle of the stars, the planets, and the influence that they could have on people. So here it's books from the 18th century, but really shows this link between macro and microcosm. We also have this is the part on the shepherds with a work of art, objects, and those books from the shepherds' calendars. We keep also a cabinet of an astrologer from Paris called Mage Bellin, which was a very famous mage in the 20th century. And when he retired in the 70s, he gave all his collection, all his cabinet for the Musée des Arts et Traditions Populaires. So we reconstructed it for the first time at Museum, really exactly as if we were in the cabinet. So it's kind of a big moment in the exhibition when you arrive in this strange interior, which is not that it looks like a classical interior from the 70s, but there is this boule de voyance, this chouette, but yeah, so we explain the boom of astrology in the 20th century, and also in the 21st century. Actually, in France, 40% of the people think that the position of the planets at the moment of their birth has an influence on them. So it's a big subject, and for a society museum such as Museum, we thought that it was important to explain that, and of course, to explain that scientifically it's not valid, but it's a big subject nowadays. And what is very interesting is that it shows that its beliefs have centuries, and they still exist, even though science, even though Galileo, Newton explained our place in the universe. So those are the kind of archives from the Mage Bellin that we present. He was very famous because he said he predicted the death of Marilyn Monroe. So it's a big moment in his career. So here it's a really like hardcore pop culture. We made a little cabinet of objects from everyday life that are very common, and that shows, it's kind of a joke in the exhibition, but we thought it was very interesting to show that those images are not actual images that were first described by the Mesopotamian in the 3rd millennium before Christ, that were represented by the Greco-Roman world, given to the Arab Muslim world, and that now are everywhere in our visual culture, in our magazines and so on. So here is the little joke on in the exhibition. And to finish, the last subject of the exhibition is to ask ourselves what is our connection to the stars today. So there is this astrological culture that is very, very important, but there is also a scientific culture. Currently, scientific research offers us an understanding of the immensity of the universe and allows us to contemplate billions of galaxies made of billions of stars and planets, and is the subject of this work by Caroline Corbasson. We saw earlier a photography from the James Webb Telescope, and here it's a very big drawing, so you can see on the right here, very big drawing of one of the James Webb photography showing tons of galaxies. And with Juliette, we wanted to show that, so that there is this science that is living another revolution, actually. But the paradox is that people on Earth can't see the starry sky. So we wanted also to focus on light pollution and to ask ourselves what is our link to the stars when we cannot see them anymore. So these are work of art from French artists Thierry Cohen, Armel Toulounda, and Camille Pradon that all three work on the light pollution. Thierry Cohen, he creates this kind of photo montage of the sky that could be seen in some cities, or here in Venice. And Camille Pradon, the one on the left, she drew a starry sky, but with all the satellites of Elon Musk that are a very big subject, actually, because the sky is going to be a big garbage because of those kind of satellites. And that's it, I think. Thank you.
Thank you so much, Guérin. I will ask Thomas to join us for the discussion. And so, do you have any questions? Yes?
Yes, Yes, for Thomas. I enjoyed very much your talk. It is not a question, it's more a remark, a translation of Blumenberg, Ersteckt. You translated, it is your translation, or perhaps a standard translation. Would it be possible to translate in intensified more than amplified? With the idea of force, yes?
Yeah, it's an
you agree?
exceptionally short answer, yeah.
You agree? So, with the idea of force, which is typically an idea of Blumenberg, that technical modernity can supply natural forces. And in this case, it is obviously the celestial light of the stars, which are intensified, I suppose.
Agreed. Thank you. Can I also pose a question?
Sure. Yes, sir.
Okay. Actually, I have like two questions that are quite obviously after my presentation. So the one would be like if there were also like aspects or objects that you would present that also would entail entertainment. It's also something that I would be really curious to see, like if this is still a thing in contemporary stuff. And what I found like really striking in your presentation, also with regards to this like night sky presentations of the architecture of the exhibition, that also kind of, for me, really resonated also with the sea, like being outside, like immediately, and also like obviously me coming from my topic where navigation and mobility is like a dominant theme. I was also wondering, because like I don't know like where all these objects came from. Some of them maybe also traveled over the Mediterranean. Is there some link or some reference or pondering on your side from your team, like on this, you know, like entanglement of the sea and the night sky or the cosmos?
It is very true because Juliette Besset, the co-curator, she specialized so she's a contemporary art historian, specialized on the sea subjects. So it was a big thing for us to make some of focus on the sea, and we made 2 weeks ago a symposium on the links between the sky and the sea at Museo. So if you are interested, we have all the captations. And so in the exhibition, there are lots of objects linked to the sea because obviously Museum is on the sea and it's devoted to the Mediterranean, so we could not talk about it. And we talked about it also with the lots of objects of navigation showing how different population oriented themselves to the night sky. That I didn't show you on this for this presentation, but it's one of the there are 6 parts in the exhibition, and one of those 6 parts is really devoted to navigation and the link between sea and the stars.
Thank you very much for the presentation. I have more curiosity to ask to Engerad. In your presentation, you show the showcases with the manuscript of Peiresc, where there are also some lenses and a telescope. Are these coming from the same the Bibliothèque d'Ingelbertin or not?
So,
yes, this one.
So the one on the right is from the manuscript from Bibliothèque Ingelbertin, where they kept all the archive of Peiresc.
Yeah, I know, because it's very important, because I know that Peiresc is the first that prepared some table to calculate the position of the satellite of Jupiter and propose as a solution for the longitude also.
Names to the satellites.
For the King of France and not Turkey.
Yeah. And so the other objects are from the City of Marseille collection. There is this observatory in Marseille that has a big historical collection, and they lend us 10 of their scientific objects. But it's not shown because it's the observatory is closed. And so their collection were presented like 20 years ago in Marseille in an exhibition devoted to their history, but now it's unfortunately kept in storage.
This is the only occasion to see them.
Yeah, but I think that they have, but we'll see what they will do, but they have a project of create a museum on with their collection, so maybe in a few years you will see them presented.
We hope.
Yeah.
It's very important because there is an important collection. The history of astronomy in Marseille is very long.
Yeah.
Thank you.
Thank you so much. Thomas, I was wondering if you're going to work on sound, because it seems to me that it's an essential dimension of the planetarium experience. Isolation of the walls is a really important technical issue when you build a planetarium, and the voice, the live voice in particular, is something that is thematized. So I would be really curious about how you see that. And I have another question about the tension between the teachings of universal astronomy and the workings of the solar system and the locality. So the Griffiths Planetarium is obviously amazing because, you know, there's Hollywood and JPL and lots of stuff going on in California. And there's a really interesting tension between the kind of standardization of popular astronomy that the planetarium does, because SAIS provides not only domes, telescopes, but it provides us the content if we want. And now we have a live, you know, very lively international market of canned astronomy. And yet there is something hyper-local about the way in which one speaks about astronomy. And the Marseille exhibition is a good example. You know, you have your Aix-en-Provence astronomer, you have your Mediterranean, the local grounding, including cultural, seems to be, you know, sort of essential and perhaps complementary to talking about something that is, in principle, possibly very universal. I'm completely fascinated by the cutout silhouettes of cities. So we've seen on the stamp with Galileo, it was the wrong silhouette. But in planetaria, at least in the old styles, you had in every city, you had the cutout silhouette of your own city. So in Munich, you could see, you know, the Frauenkirche, and there's just so much care put into little cutout cardboard when at the same time you're, you know, talking about this amazing technology that makes you travel in space and time thousands of years, and yet the kind of local grounding of the skies above our heads and the history of looking at the sky here and in history seems to be really important. So I would love to hear both of your thoughts on that issue.
Shall I start? Okay. Actually, I still have to do some more like archival research for the Griffith Observatory in regards to the audio installations. I read that there were audio installations. I'm not 100. I knew that there was music, but I cannot specify as to yet. But I know that it was quite influential that before they did this at the Griffith Observatory, they started at some observatory in San Francisco to do like concerts and stuff in there. So that like was apparently for the region, like it was kind of groundbreaking that they used it as a musical event venue, and that kind of influenced apparently also what they later wanted to do at the Griffith Observatory. And with regards to the like cosmical local relationship, I would say that this is, to my understanding, not so much in the planetarium itself in the Griffith Observatory, but it's quite obvious. I tried to hint at this a little bit at the Bellin murals, where like the entire history of science is situated in Southern California. And this is like not, and this is also, to my understanding, a little bit a like a mirror or like an argument in an inner American like competition field, and this is a competition for for the entire United States, like where are the important facilities, where are the companies that can contribute to the space race, where are they situated, where are, you know, like because they struggle for this, like who gets like the commissions, the big commissions from NASA. So, and this is also like an argument, like this is happening here because like California, it doesn't come to mind yet, like immediately that they wanted to do this. And actually also they tried to, maybe this is also an interesting note on this, in this regard, that already in the early 60s, there was a town meeting that I found some archival stuff on, that they wanted to do the first space age museum in California, and there's a lot of like arguments in the documentation of this, that they like wanted to make this argument that like the space race, actually the stuff that from the states is contributed to this, it's all coming from California. It's the most important state for this. Quite interesting. So this is, maybe this like resonates a little bit with your question.
For the museum exhibition, we really wanted to focus on the Mediterranean and especially on the Provence and Marseille region, because there are two important observatories that still exist in Provence, in Nice and in Saint-Michel l'Observatoire, which is really nearby. And we thought it was very interesting to work with them because they could lend us some very amazing objects, but also because at the very beginning of the exhibition we talk about the light pollution, and the light pollution is very important in the Mediterranean. It's one of the most impacted regions in the world. So we thought that it was very important to localize the objects that we had, to talk about people from Marseille, from the region, from Provence, like Peresque, to explain what you can see without the light pollution, what people in the region saw without the light pollution.
I only have a very brief comment. If you can go back to the slide where there is the painting by Vermeer and the other portrait of the astronomer. Yes, because I have listened to a French podcast on France, France Culture. It was
the one with Patrick Boucheron and making an interview with Juliette Besset,
yes.
which is like a curator.
And it was amazing. And then I saw your name in the program, and I was like, "Well, what's happening?" Okay. And I think that what she said about the Vermeer portrait of the astronomer is like perfect for the theme of the conference, because I remember that she underlined that Vermeer portrays an astronomer who doesn't look at the sky, but he looks at the celestial globe. So it's perfectly consistent with the theme of scaling the cosmos we have been talking about today, and it really resumes very well why we do need to scale in the sense of measuring and scale in the sense of reducing to our senses the cosmos. And that's why Vermeer's astronomer looks at the celestial globe and not at the night sky.
Yeah, it's very true, and you can see also that he makes this kind of gesture with his hand like a compass.
Yes.
Thank you very much, Ilaria. This is such a great conclusion for this day. I'm going to send you all an email with the address of the restaurant. And no, because otherwise, sorry, I was thinking about the cosmos, but we need to focus also on the here and now. But anyway, the address is Via della... Okay, at 8. 10 to 8, then we meet at 10 to 8. Thank you, Giorgio. Okay, so I think that do you have any other questions or remarks? No? Okay, so I want to thank really warmly all the speakers of today. Thanks. And see you tomorrow. If you want to, well, have a look at the museum or whatever.